Okay, thank you. Let's see here. Hold on. Okay, went too far. Okay, thanks. So today I'm going to talk about Deep Tensor and our experiences using Graph AI for enterprise business problems. So to start, what I'd like to do is kind of set up kind of how we see graph versus relational data. So when you think of, and some of you, this might be old news. Some of you, you might be focused more on other parts of AI, and this might be new. So kind of when you do, a lot of business data is traditionally stored in relational databases. So if you look at kind of a relational database, the core is you have a table and you have records in it. And graphs are different. And when I mean graphs, I'm talking about the mathematical graph with nodes and edges, not charts, right? So the core piece of that is you have nodes and edges, and it's kind of less structured. But it can express kind of more complicated relationships than you can with relational database. The query languages, so relational databases have kind of standardized on SQL. Everyone knows that. It's still a little more open in the world of graph databases. The one we use is Cypher, which is associated with Neo4j, and I think there's also other implementations as well. Popular data stores, there's, obviously in the relational database world, there's Oracle, SQL Server, Postgres, all those kinds of things. In the graph world, there's also multiple data stores, both for commercial and open source. And again, we're kind of focused on Neo4j, but there's others out there as well. And Neo4j is both open source and commercial and hosted. So analytics, when you think of analytics in a relational database, or like a big data environment like Hadoop or Spark, you're thinking of kind of doing joins between tables, aggregations, group by, halving, and you might be doing kind of multi-dimensional analysis as well. Graph analytics are very different. These are things like finding paths through the graph, finding nodes that are kind of influencers, which is called centrality, or detecting kind of subgraphs that are kind of tightly connected, which is community detection. So these are some of just a small sample of the specific graph analytics you might do. In machine learning, so if you're taking relational data, some of the most popular open source frameworks are like, TensorFlow and PyTorch. For graph machine learning, it's a more new area, and so there isn't kind of like a well-defined framework there. You can kind of take the graph data and try to fit it into one of these traditional things. And Fujitsu has kind of produced a new kind of graph technology that works directly on graph data called Deep Tensor. Okay, so next let me talk a little bit about some different kinds of graph machine learning. And so we have unsupervised learning, and that includes that's where you have a bunch of graphs that you don't have any ground truth, and you're trying to put these subgraphs into different categories, right? And so it's trying to look at the structure and say, are these more similar or less similar? Another type of graph machine learning is link prediction. You see this a lot in social networks. I'm trying to say, I know that these people are friends. Will they be friends with someone else? That kind of thing. Classification. So this is more about where we say, I have different kinds of graphs, and I have a ground truth where I can provide some kind of label for the graph, and we'll see a bunch of examples of that. And so I'm going to label those. And that's what the machine learning should figure out, is those labels. Regression is how I have some number, usually like a score, and want to apply it to this. And so we're going to be focusing on classification and regression, and because these are the focus of Deep Tensor. So a little bit on why it's hard to do graph or machine learning. So if you have a neural network, and typically what it has is it has a fixed structure. So you have a fixed number of inputs, you have a fixed number of layers, and each layer has a certain depth, and they're usually fully connected, and you're kind of, what you're training is the weights of these layers, of these connections. And so if you have an image, if you have like a relational table, you have a bunch of samples and you kind of feed all those in. That's fairly straightforward. For images, it took a little longer to kind of get to that point, but you can think of, there's a lot of standard ways to say, I'm going to rotate and crop images and get a bunch of images that are the same size. So like 28 by 28 or 256 by 256 pixels. And so once you have those pixels, you can kind of map those pretty straightforwardly to the inputs. And there's also special layers like convolutional layers which can be used to kind of find different pieces of the image. And so because of that, the image detection is not very sensitive to the exact kind of details of that image. For graphs, it's less understood, because if you're passing in a lot of graphs, each subgraph may have a different number of nodes and edges. And so how you map that is kind of challenging, and is very sensitive to how you map that. So that's a problem. And that's kind of the problem that Deep Tensor attempts to solve. So this is what Deep Tensor is. So Deep Tensor basically, at its core, it has a neural network and then has a layer in front of it. And this is called a core tensor representation. And so what it's doing is it's taking your graph data as is and then mapping it to this fixed size, multi-dimensional representation, and then passing that into the neural network. And kind of how this works is it starts with a very naive representation. It passes it into neural network, and it gets back, then it basically runs through the data, and it comes back with classification errors. And so typically in a neural network, you have this back propagation step, which is looking at the errors and trying to minimize the errors through some kind of solver. And that is going to, and so basically that's how you tune the weights of your neural network. So what Deep Tensor does is it adds extended back propagation. So it's tuning this core tensor representation and fine tuning it based on the classification errors. So then each epoch that you go through the training, you're not only training the neural network, but this graph representation. And so you can think of it in a way as a graph embedding, if you're familiar with those, and it's being automatically tuned to take this generic graph data and find the kind of most relevant parts for the particular questions you're asking the machine learning. Then in the end, it also has an explainability piece, so it can give you kind of an explainability, and it's using kind of underneath the covers the Lime technology, if you're familiar with that, from the University of Washington, but that is being used in the context of graph, and we'll see some examples. And so this is based on some research. So we have kind of a research lab, and we have real research based on this, and so and the research is ongoing. On top of all this, we built kind of what I would call a ML development workbench. It's called Accessible Deep Tensor, and what it does is it can let you import data into the tool, and it has a GUI, and you can define a graph on top of that, which we can then generate a Neo4j instance and let you explore the graph. We can then do analysis of that data and come up with recommended configurations for Deep Tensor, run Deep Tensor, and visualize the results. And the end result is a trade model. So, and Wing is going to give a demo for that in a few minutes. So I'm going to talk real quickly about two use cases that we've used it for. We've done a bunch of others, but there's only time for two here. One is in network security. So the idea is that you have a bunch of logs of connections between machines, and they have a timestamp, and they have a flow ID, which is basically source IP, destination IP, and related things. So we can represent this as a graph. So for example, each IP address becomes a node of the graph, and edges are those connections, and all the metadata become properties on these edges. So when you do this, you can see different patterns. And so we have a traffic generator that simulate different kinds of traffic. So here's kind of random traffic, and you can see it's not truly random because there's kind of client server interactions between these nodes. This is a port scan where one node is scanning all the ports of different nodes, looking for vulnerabilities in those nodes. This is a denial of service attack where it's kind of all these nodes are attacking one other node. So these are, when you view it as a graph as opposed to as a log, these become a lot more obvious. Though they're less obvious in the real world because, which is why you need the machine learning, because this might be like 5% of the traffic, not like 95% of the traffic. So with Deep Tensor in the original paper, they did use this, there's a famous DARPA intrusion detection data set. And so it was, did work using that and improve the accuracy. We've also done a lot of work with synthetic data sets, and that's ongoing work because we expect that as you add more features, you can get better results. And the explanations we get out of deep tensor are very intuitive. So this is one of the explanations we get back. So this is showing a visualization of a denial of service attack. This node here in red is the middle of the attack. And what you're kind of seeing is you can see all the other nodes are attacking it. The red nodes mean, and red edges mean that it's more likely to classify it as an attack versus normal traffic. And the blue nodes are ones that are less likely. And as we see, kind of this background traffic here are all blue nodes, and kind of the center of this is a red node. Oops. Okay, so let me talk real quickly about another use case. So we're interested in fraud detection, and we're working with Laris actually on some use cases involving credit card fraud detection and the money laundering. And kind of, there's not a lot of public data available, so we've been doing work, I mean, a lot of public data available, but one that's very similar is there's a data set. Medicare is in the United States, it's a government provided medical system for the elderly. And the way it works is that because we have a private healthcare system, is that providers, which are doctors, are basically someone goes to see a doctor, and then the doctor will bill the government, and the government will reimburse them for the expenses. And so that data is available publicly, and there's another data set which says who has been blacklisted from the system for fraud. And so we can combine those together, and we can do represent this as a graph, and we can do machine learning on this. And to show why you might do this, this is kind of what the raw data looks like. And so you have a provider that's the doctor. You have data for, we have data for like 5 years. And we have different procedures they might perform, like take an exam, surgery, testing, that kind of thing. And then the rest of the data, we don't have individual transactions. We just have aggregated data. So how many people they received this procedure and how much was billed in total. And then we have fraud information. And the fraud information is really for the provider themselves. It's not for an individual procedure, right? So when the government blacklists someone, they don't say, we're blacklisting you for exams. They say, oh, you're being blacklisted completely from the system. And so if you're looking at it from traditional machine learning, where you have just these, you're looking at one row at a time. And so you have to treat each row independently or figure out some way to combine all this. With graph machine learning, you can view this as a graph. So we can have edges from the provider to different procedures, and then the other aggregated information that become properties on this. So this is a much more natural way to do it. And we can label each subgraph then as either fraud or not fraud based on the classification of that provider. So before the demo, real quickly, I'll talk about a few real world challenges we've seen in kind of our work and kind of how we are addressing those. So first one is large production databases. So like particularly in finance, they have production databases for graphs with billions of records or billions of nodes and edges. And kind of for graph classification, we need to kind of split those into individual subgraphs. So kind of that's kind of how you do that is still kind of an art. And so what we've kind of been developing a methodology. It kind of involves understanding the data model, understanding how data is distributed, and the data distributions are a little different than you might see in a relational model. So you got to kind of look at these relationships, and some nodes might have like a lot of connections, some nodes might have few connections. So understand that, then figure out how you divide things into subgraphs by picking a unique identifier. So for example, in the network attack scenario we looked at, we're actually dividing it into time intervals of 10 minutes. And so we're looking at the entire graph for 10-minute intervals and seeing how it evolves over time. For the Medicare fraud scenario, we're actually looking at an individual doctor and all their procedures they performed, and that's the subgraph. So that's kind of deciding that is kind of the first step, and then we can extract those subgraphs from the source graph then. Another issue is that not all relevant data fits into a graph, and so we have to deal with things like quantization of fields, and we're also looking into hybrid techniques of combining graph ML with traditional techniques. And the third issue is bias and sampling issues, particularly like with fraud. you might see you have like a very few cases of fraud and a lot of cases of non-fraud, and how you do your sampling could affect your results and what the machine learning is actually learning. And an interesting story here, we were working on this Medicare data set, and my colleague Wing was looking at it, and we were actually working off of a published paper from another research institute, and we're kind of using the same sampling techniques they were doing. And Wing was looking at these explanations we were getting back from Deep Tensor, and this is one here. It's kind of small, but on the notation in red is showing that the features that it was using for making decisions were gender and year, and you would not expect those to be important in deciding whether someone is fraud or not. So what that kind of clued in is that the way we're doing our sampling based on the original paper was actually learning on the wrong thing. And basically what's happening is we had 5 years of sample, but if someone in year 2 got thrown in jail for fraud, then they only had 2 years of data. And so the machine learning was learning the wrong thing. So then what we did is we adjusted our sampling technique, and then we're getting kind of more accurate. The results are not as good, but we're actually learning on the right thing. And what that means is that if we put something like this in production, we should expect it still to work. Whereas if you went on the original thing where there was bias in the data, it's not going to do very well in production. Okay, so that's kind of the high level. And so I'm going to hand it over to Wing, who's going to give you a quick demo. So Wing?
Okay. Let me see. Hold on. Can you hear me okay?
Yes.
Okay, good. Okay, so
Yes.
my screen. Good. So right now, on my screen is the web browser to the web app, which Jeff has shared before in the slide. It's called Accessible Deep Tensor Tool. So Deep Tensor is the Fujitsu Japan technology that they created to run Graph AI. So this tool is really like a user interface for people to explore the data and kind of like configure it differently before it will be fed into the Graph ML technology for Fujitsu. And then we'll also provide graphical view of the explanation and all that, so that it will be a way for you to look at the data first before deciding what to do next about the real learning. Okay. So the layout of the tool is kind of like this. On the left hand side, you'll see a column of all the steps you'll go through from end to end. So we'll start with like data set that hasn't been looked at, and we'll go through all the multiple steps until we go through the training and get all the explainability part. And the middle of the panel will be kind of like specific to the steps that's being done, and it will show different things. Okay. So the first thing is that we can either upload data into the tool to do analysis, but for the sake of the demo, I'm just going to do pick one that we've already been introduced into our system before. So there are different data sets that we've looked at, and I'm going to focus on the network attack one. But as you can see, the Medicare one Jeff mentioned about, we also do machine learning on commercial lending data, and also like medical genomic data. So these are all different areas that we've tried, and we've packaged some of these data sets into a small usable data set that when we pass out the demo, people can actually easily take a swipe at it. So the network data that Jeff talked about has a number of subgraphs. It's only free limited. It's like only 50 subgraphs in there. 25 of them are in the fraudulent case, basically normal traffic, and 25 of them are in a network attack scenario. And each of the subgraphs are being grouped using a 10-minute time slice, and it has like the source destination, IP address, port, and type, and so on. So this is like really just a quick overview of the data. If you go to the next step, the visualization, we embedded this tool called Google Facets so that you can actually see kind of explore how the data actually looks like. And it also have these nice feature where you can actually visualize how the different columns are interrelated to each other. A bunch of guys here probably have used this before, so I'm just going to quickly walk through this. So at this point, I mean, all the data that we have, we are going to put in the system is encoded as CSV files. So at this step, we will try to build the CSV-based data into Neo4j graphs. So for the network attack scenario, obviously, as we have shown, we'll use the source and the destination IP address as the 2 nodes. And we'll label the class as either normal or attack based on the graph labeling that we've also passed into the system. And for simplicity, I'm just going to use the destination port as the general feature. So obviously, the more feature we add into the graph, the more data you get to learn on, but also obviously learning will take longer. So let's just keep it really simple right now. So right now, the Neo4j database being created with the CSV data that we have. So that's one way of operating where we actually take like table data and import into the graph so that we can do learning. The other approach that we also try to do is like from a native Neo4j graph database, we'll try to extract like the subgraphs directly from the Neo4j data and then represent it into the Tensor. So, which is basically the approach that we're working with LaRousse right now, so that we can actually natively analyze data that are sitting in a graph database. So that step is done. And as you can see, we can actually go through a quick visualization on how the subgraph actually look like. So this is from what everybody can easily see, like a lot of nodes are talking to a single node within this 10 minutes. So most likely this is a attack scenario. And if I look at some of the other data, so for example, on this guy, this is kind of like a more regular non-attack scenario will look like, where a lot of nodes are like randomly talking to each other, right? And so this is like a very basic viewer that we put into our ADT tool, but the whole Neo4j database can also be looked at in more detail, where obviously you can see these are basically the same subgraph that we showed just now, but they are also viewable in Neo4j. And you can actually make changes to the queries so that, for example, you can get like a much better view of what things are. And you can actually change some of these parameters in the query so that you can get like a different look at the same data, or maybe like bring out some of the more unused features and kind of like query them differently. So once we have generated all the subgraphs, they are ready, we're ready to do the testing part, okay? In order to do the testing, we have to convert them into what we call the core tensor. Basically, we take the graph, which is represented as nodes and edges, and convert them into these multi-dimensional array core tensors before we feed into the neural net. So this part of the tool is basically the conversion of the graphs into these tensor, okay? And we have some heuristic we put in the tool. So we basically say which are worthwhile being used as dimensions and which might not be used as dimension. Again, the more dimension that we have in the tensor, the more complex the learning will be, and it will take longer. Obviously, if you have like pick the right features, it will generally yield you good results. But if you end up like picking the wrong features or useless columns, is just basically creating larger tensor dimensions size without helping in your accuracy. So this part is really heuristic to help avoid those kind of situation. And as we can see, what the tool is kind of saying, maybe like we don't need to use the label as the learning. So maybe we can just like use just the source and destination nodes and rely purely on the graph structure to do the learning. So at that point, after we go through the heuristics, we can actually configure the tensors themselves. I'm going to ignore the recommendation because I know we'll get a little bit different information if we actually use the port number as well. So in the choice, we can actually choose what the dimensions are for the tensors. And they can either be chosen as like local value, where we just basically use the graph structure itself and not care about the values, or we can actually assign a global value to them. Like for example, like in all these network scenario, I mean, the source and the destination IP address might not matter that much in determining whether an attack is going or not, but the port actually will convey some important information on whether it is like an attack scenario or not. So I want to keep that as a global parameter. So there's a little bit more configuration that we will explain in our documentation. And the key is that you have to select how many epochs you want to run the training on. And I know for the simple data set, 20 epochs is enough to get me decent separation. So after we go through this phase, right now the data is being converted from the graph to the tensors. We split the data into training and tests, and we'll get ready to actually do the learning itself. Questions so far? There'll be like 2 more steps and then we can open for some questions. So at this point, the tensor has all been created and we're ready to run the neural net on the tensors. So as you can see, as this get run, there's good converging going on. And because the data is really simple, the testing fits real well. I mean, we definitely is easily able to classify the positive and negative cases. So now we take part of the data that we had saved for the testing and feed it through the model and see what number we get. And this doesn't take very long. And as you can see, the negative cases, meaning like the non-attack cases, are being classified very well. And the positive cases, meaning the attack cases, are actually also classified very well as well. So that's one false negative, meaning there was one graph that was an attack and we wrongly classify it as a non-attack. And we can use the explain data to see why is that so. And for most all, we can also look at all these other cases and see why the AI is doing this classification and see whether as human we agree to its decision. So to do that, there's another step you have to do to run the LIME technology on the data. So when the explain is completed, we can go to the visualizer for the explain. So what the explain part does is that it would create all these different scores. So every edge and every node will be scored as far as how they contribute to the machine learning's decision whether this is a positive or negative case. So as you recall, these are like the confusion matrix, the 8 different test cases we have. And if I look at a true positive test case and show the graph. Okay. So this is similar to what Jeff had shown in the graph, but with a little more detail. So as you can see, there are a bunch of edges that are colored red, and this is actually the scoring for a positive identification. So everything that is shown as red, either being a node or an edge, is an indication that the machine learning thinks this is the reason that we consider this graph as a fraudulent attack scenario. So the middle node get talked to a lot, and this is a good indication that this is an attack. Some of the edges are marked red as well, and the nodes that are connected to it are also marked red. So these are probably nodes that would also generate more attack traffic compared to other things. And you can also see the port number in here is very common among all these different clients that are talking to the server. And they are all reasons that the machine learning believe that this is an attack scenario. And if you go ahead and try to look at one of these non-attack scenario, so visually, yes, it will look very much like our label data. But if you look at the coloring of the nodes, now we are showing the reason where we think this is not an attack, and like the different kind of port numbers, and like none of the nodes particularly will tell me that this is a attack scenario. So if we look at one of these false negative, so this one particularly is labeled as a non-attack, and I'll probably have to find some of the reason why the machine learning thinks so. And as you can see, machine learning pretty much say that because there are these traffic to these particular ports and they are red, it is the main reason that the machine learning thinks that this is not an attack scenario. So at this point, it's kind of like, do I agree with what the machine learning tells me or not? And if I don't, it probably means that I have select my columns or my features, or I configure a feature possibly wrong, like Jeff has mentioned in our Medicare test scenario. So this is like the time where the data scientists actually come in and challenge the machine learning, and basically, and also challenge himself whether I did a good job defining the data for machine learning. And by refining our assumptions and how we actually configure the data before feeding it into machine learning, hopefully we'll get to a case where most of the positive and negative cases agree with what we humanly think. And then we can use that to say, this is like the correct model. We'll build confidence this is the correct model, and we can use it in production data. Okay? Any questions?